Let's take a look at the concept of formal charge. It's a bookkeeping way of telling whether an atom is electron rich or electron poor. So let's look at a couple of possible scenarios for an oxygen atom, let's say. This first one is what we said normally occurs for an oxygen atom. Normally it has 2 bonds and 2 lone pairs. And that is the most stable configuration for oxygen. So I've just kind of like drawn a little wall. We're not sure what the oxygen is bonded to, but each of these bonds is a shared pair of electrons. So of these 4 electrons that are being shared, if they're shared evenly at least, oxygen has 2 of them. So we have 1, 2, 3, 4, 5, 6. So these are the 6 valence electrons that oxygen had when it started. It still pretty much has access to all 6 of those. So the formal charge here would be the valence electrons that oxygen brought. So it brought 6 electrons. Then we're going to subtract the lone pair electrons. There's 1, 2, 3, 4 lone pair electrons. And then you're going to subtract half the number of bonding electrons, which is the same as the number of bonds. So here, in this case, there are 2 bonds, so there are 4 bonding electrons. We can divide that number 4 by 2 and get 2, or we can just count the number of bonds and get 2. And the formal charge comes out to be 0, which means that oxygen is sort of neutral. It has the same 6 electrons that it brought. It's still using them. Oxygen in this scenario, if you kind of look, if you think about this oxygen as having half of this bond, it has 1, 2, 3, 4, 5, 6, 7 electrons when it only brought 6. So this oxygen has access to more electrons than it brought to the compound. So the formal charge here would be the 6 electrons it brought minus the 6 lone pair electrons that are drawn on here minus the 1 bond that it has. And that would be a -1 formal charge. So this oxygen is kind of negative compared to how it started off with before you put it into the compound. It's sort of got access to 1 additional electron that it didn't have before. It's somewhat negative. Oxygen in this scenario, you can kind of see if it has half of each of these bonds, 1, 2, 3, 4, 5, it has fewer electrons than the 6 that it brought. We have 6 minus the 2 lone pair electrons minus the 3 bonds. So we have a +1. This oxygen has a little bit of a positive charge to it compared to what it had when it was being put into the compound. It had 6 valence electrons. Now it really only has access to 5. So it's sort of a +1 formal charge. So atoms are the most stable when they have a formal charge of 0, which is why we say that oxygen, in most compounds, we should draw it with 2 bonds and 2 lone pairs because that is what it prefers. Let's take a look at these structures. We have ammonia. So this is something that you kind of have to draw the Lewis structure and not just look at the formula because you need to know how many bonds and how many lone pairs this has. So we have nitrogen. The formal charge on nitrogen is the 5 valence electrons it brought minus the 2 lone pair electrons it currently has minus the 3 bonds or half of the 6 bonding electrons, which would also be 3. So that is 0. So nitrogen is fairly stable. We mentioned that nitrogen does like to have 3 bonds and 1 lone pair, so that's a stable situation for nitrogen. Hydrogen has the 1, each of these is pretty much in the same scenario, so we could just do the hydrogen once because it's the same for all of these. They all brought 1 valence electron, they have 0 lone pair electrons, and they have 1 bond. So we have a 0 formal charge on each of these hydrogens as well. Okay, so here we have the ammonium ion. Nitrogen brought 5 valence electrons. It has 0 lone pair electrons on it in this structure, and it has 4 bonds. So that is a +1 formal charge. The hydrogen brought 1, has 0 lone pairs, and has 1 bond So that is a 0 formal charge. Let's go ahead and write the formal charges on these atoms. So we got 0 all over the place here. And they all add up to 0. And overall the charge on the ammonium is also 0. So the sum of the formal charges is going to be the charge on the structure itself. So if we look at these guys, these hydrogens all have 0. And the nitrogen has a +1 charge, formal charge. So the positive charge that's on this ammonium ion is mostly living, quote unquote, living on this nitrogen. So that's where that charge is located. The nitrogen is the element or the atom in this structure that is electron poor. All right, let's try drawing a Lewis structure for carbon monoxide. We haven't seen that one before. This is kind of an unstable, strange structure. We have a total number of valence electrons being 10, 4 from carbon, 6 from oxygen. So we've used up 2, 4, 6, 8, 10. We need to get some multiple bonds going here so that the carbon can have a full octet. And we end up with this type of structure here. The formal charge on carbon would be the 4 valence electrons it brought, minus the 2 lone pair electrons that are sitting on it, minus the 3 bonds. So we have a -1 for carbon. Oxygen brought 6 valence electrons. It has 2 lone pair electrons on it and 3 bonds. So that is a +1. So this particular Lewis structure has carbon with a -1 formal charge, oxygen with a +1 formal charge. So neither one of these are completely happy. It's a sort of unstable molecule. Even though the Lewis structure is perfectly valid, we do have the right number of valence electrons, and we have the a full octet around each atom. So there's nothing wrong with the Lewis structure. It's just overall having some formal charges is less favorable than having a molecule like this where they all have 0 formal charge. So sometimes you can have several possible Lewis structures that have nothing wrong with the Lewis structure. So the Lewis structure itself has the correct number of valence electrons, has octets around the elements like it should, but maybe you can draw a few different possibilities. And you can use formal charge to figure out which is the better Lewis structure out of some different possibilities here. If you can draw one where all the formal charges are 0, then that is definitely the best. That's not going to be possible if we have an ion like this one down here. We can't have all the formal charges be 0 because then it would add up to 0, and where would this -1 charge come from? So it's not always going to be possible, but if you can, that would definitely be best. If you have to have some formal charges, try to keep the smallest number that you can, and keep them as small as you can. Like if, it's better to have a +1 and a -1 than a +2 and a -2. If you have adjacent charges, if they're 0 or the opposite sign, that would be better. So having a +1 charge next to a 0 or next to a -1 charge would be better than having 2 +1 charges next to each other. And another consideration, if you have a +1 and a -1 that you have to put onto something, it's better to put the negative charges onto the atoms that want electrons more, the more electronegative atoms. So those are some considerations. Let's go ahead and see if we can use the formal charges to figure out which of these 3 is the best possible choice for carbon dioxide. I know we've worked with carbon dioxide before, but we have some alternate Lewis structures that can be drawn here. So let's see why the best one is the best one. And the same thing here, we'll use some formal charges here. Okay, the formal charge on this oxygen's actually looking good. It has 2 bonds and 2 lone pairs. So not surprisingly, we have the 6 that it brought, the 6 valence, minus the 4 lone pair electrons, minus the 2 bonds. So we have a 0 formal charge here. For this one, we have a formal charge of the 6 valence electrons it brought, 0 lone pair electrons, and 4 bonds, so we have a +2. This one we have carbon with 4 valence electrons, 4 lone pair electrons, and 2 bonds, so we have a -2. So this is maybe not ideal. We have some formal charges. We also have our negative formal charge on carbon, which is less electronegative than oxygen. Oxygen would prefer to be negative, so this is not too great. Let's take a look at this one. We have 6 valence electrons, 2 lone pairs, 3 bonds, so we have a +1. This one we have 4 valence electrons, 0 lone pairs, and 4 bonds, so we have 0. This one we have 6 valence electrons, 6 lone pairs, and 1 bond, so -1. So this is better than the first one because we have smaller formal charges, and also they're kind of separated from each other, so that's pretty good. The negative is on the oxygen rather than the carbon, so that is better than the first one. Let's see if we can do better still, however. We have 6 valence electrons, 4 lone pair electrons, and 2 bonds, so we have 0 on that oxygen. Carbon, we have 4 valence electrons, 0 lone pairs, and 4 bonds, so we have 0 for that one. And here, this is pretty much the same as the other oxygen. We have 6 valence electrons, 4 lone pair electrons, and 2 bonds, so 0 on that one. So we have all 3 of these atoms in their most stable configuration that they like with 0 formal charges. We have the oxygens with 2 bonds and 2 lone pairs, which we mentioned is best for oxygen, and carbon with 4 bonds and 0 lone pairs, which is best for carbon. So these best case scenarios are the scenarios that give formal charges of 0 to these particular elements. So let's get a nice circle around this one. So that last structure drawn is definitely the best structure for carbon dioxide. All right, let's try something a little bit less familiar than carbon dioxide. Here for the carbon, we have 4 valence electrons, 4 lone pair electrons, and 2 bonds, so a -2 formal charge there. For sulfur, we have 6 valence electrons, 0 lone pairs, 4 bonds, so we have a +2 there. And for nitrogen here, we have 5 valence electrons, 4 lone pairs, and 2 bonds, giving it a -1. So -2, +2, and -1 add up to -1, which is the charge on the ion. But these are some pretty significant formal charges. I'm thinking that we might be able to do better with one of these other structures. So for this nitrogen, we have 5 valence electrons, 4 lone pairs, and 2 bonds, so that's -1. For the carbon, we have 4 valence electrons, 0 lone pairs, and 4 bonds, so we have 0. And for the sulfur, we have 6 valence electrons, 4 lone pair electrons, and 2 bonds, which is 0. So this definitely is better. We have -1, 0, and 0. And we have the -1 on the most electronegative element, so I think that looks promising. So this last one is pretty much the same as this first structure for the carbon. We have 4 valence, 4 lone pair electrons, and 2 bonds, so that's a -2 charge again, just like it was over here. For this nitrogen, we have 5 valence electrons, 0 lone pairs, and 4 bonds for a +1. And then for the sulfur, we have 6 valence electrons, 4 lone pair, and 2 bonds. So we have a 0 there. So we have formal charges of -2, +1, and 0. Which I think looks better than the first structure, but the second structure still seems the best. It doesn't have to have a -2 on the carbon. It has just a -1 on the nitrogen. I think that's way better. So we have this middle structure being the best for this ion. Let's go ahead and use formal charges to figure out which structure would be better for the phosphate ion. So the phosphate ion, PO4 with a -3 charge, has a total valence electrons of 32 valence electrons. So I have these two possible Lewis structures drawn. Both of them have 32 electrons showing. The difference is that this structure has octets around all of the atoms, whereas this one has a hypervalent phosphorus. Remember, if an element is in the third period of the periodic table or beyond, like phosphorus is, it can be surrounded by more than an octet of electrons. This phosphorus is surrounded by 2, 4, 6, 8, 10 electrons rather than just 8. So if this were nitrogen, that would be too small. It would not be able to do that. Nitrogen is the element right above phosphorus. So if this were nitrogen or any other element in the second period, this would not be an option. But since phosphorus is in the third period, this is an option. So let's look at the formal charges here. All of these oxygens are the same. So I'll just do the oxygen once. We have 6 valence electrons, 6 lone pair electrons, and 1 bond. So this would be a -1. And the phosphorus has 5 valence electrons, 0 lone pairs, and 4 bonds, giving it a +1. And so all these formal charges add up to -3, which matches the charge on the ion itself. All right, so for this structure over here, there's 2 different kinds of oxygen. I'll just go ahead and do this one once and this one once. So these are the oxygens with the single bonds. They have 6 valence electrons, 6 lone pairs, and 1 bond, so that's a -1. This oxygen has 6 valence electrons, 4 lone pair electrons, and 2 bonds. So that is 0. That's the way that oxygen likes to be. And phosphorus is 5, 0 lone pairs, and 5 bonds. So this is also 0. So here we have a structure that has the least possible amount of formal charges. We can't have no formal charges because we do have a -3 charge on the entire structure, but we have this structure, which is the accepted structure for the phosphate ion, because phosphorus is totally fine, forming a hypervalent atom, and because this minimizes the amount of formal charges that you would have to have on the structure. So this is a better structure for the phosphate ion. So let's also look at the concept of resonance. We have a Lewis structure for the carbonate ion, or we had one that we drew earlier. Let's go ahead and redraw that. So this is a perfectly good Lewis structure that we drew earlier. It has the correct number of valence electrons. Each of the atoms has a full octet around it. But this structure implies that this oxygen is related differently to the carbon than these 2 oxygens are. So it has a double bond to carbon, which would bring it in a little bit closer to the carbon than the other 2 oxygens. Also, if we look at the formal charges of all these atoms, I'll let you verify that and figure out the formal charges, but we have the negative charges of the ion concentrated on these 2 oxygens and not on this one at all. And when we look at the behavior of the carbonate ion, it is more symmetrical than that. Instead of having one oxygen be 0 charge and the other 2 be -1 each, the -2 charge is evenly distributed around the molecule or around the ion. And also, we do not have one oxygen being closer than the other 2. So this Lewis structure does not completely indicate the kind of behavior that we see in reality for the carbonate ion. It's actually a lot more symmetrical than this Lewis structure would imply. If we average this first Lewis structure with this second one that has the double bond to this second oxygen and this third one that has the double bond to this third oxygen, the average of these structures has all of the oxygens evenly distant from the carbon, and that distance is somewhere in between the distance that you would expect for a double bond and the longer distance of a single bond. So it's like each of these carbon-oxygen is a 1 1/3 bond, rather than two of them being one single bonds and one of them being a double bond. We have all of them being even, like a 1 1/3 bond, like you would get if you averaged all three of these structures. And the same thing with the charges. If we averaged all three of these structures, we would have the negative charge evenly distributed around the 3 oxygen atoms instead of concentrated on 2 out of the 3, like it would be for any single Lewis structure drawn here. So I read an analogy once that resonance is kind of like a medieval traveler who saw a rhinoceros for the first time, and when he was trying to explain what it was to his friends, he said that it was something in between a dragon and a unicorn. So dragons and unicorns don't exist, and what does exist is something that's in between two imaginary beings. So that's kind of what these resonance structures are. None of these 3 resonance structures actually is the real carbonate ion. The reality is an average. It's something in between what all of these Lewis structures indicate. It's something that can't be represented with just one true, well-drawn Lewis structure. It's more of an average of these 3 valid Lewis structures. So a lot of times this happens with symmetric molecules like this, or this, in this case it's an ion, so it's kind of symmetric, the carbon with 3 oxygens. The Lewis structure indicates that they would not be even. 2 of them would be single and 1 would be double, and that the formal charges would be concentrated on 2 out of the 3, and in reality it's more symmetrical than that. But the more symmetrical version cannot be drawn as a valid Lewis structure that obeys all the rules of Lewis structures. So that's where we get resonance structures.